Hi there, welcome back. We are going to explore rate laws, including elementary forward, reverse, and overall rate equations. The equation that I'm going to mainly focus on is the formation of nitrogen dioxide. Fun fact, nitrogen dioxide appears as a reddish-brown gas or a yellow-brown liquid when it's cooled or compressed. It has a very, very low boiling point, which is very, very cold, and hence can be used as a coolant. Let's define the rate of reaction. It can be defined as the speed at which a chemical reaction takes place at, and it's usually calculated using concentration over time. In the coming examples, we are going to look at rate law for non-elementary, rate law for elementary, and the most common one, rate of reaction, represented as concentration over time. We are going to look at the appearance of the products and the disappearance of the reagents. When representing your rate law, your equations can either be zero order, first order, second order, or third order, and each have their own respective units in which they are measured in. If the rate is represented using a negative sign, it indicates that the reaction is being consumed, and if it's a positive sign, we are forming the reaction. What is a non-elementary rate law? The stoichiometry of the reaction order of each species is not identical to the stoichiometric coefficient of the species of the reaction. Hence, we need to calculate the unknowns, which are the powers. In this case, our alpha and the beta. But what is an elementary rate law? Well, an elementary rate law simply means the reaction order of each species is identical to the stoichiometric coefficient of the species of the reaction. And by stoichiometry, we are basically referring to the number in front of your chemical when your equation is balanced. For example, we have nitrogen and oxygen to form nitrogen dioxide. Notice that when your equation is balanced, you can put a 2 in front of your oxygen, and that is our stoichiometric coefficient. Hence, an elementary rate law equation of nitrogen dioxide can be represented as this, where the reaction is second order in respect to oxygen and first order in respect to nitrogen. The overall reaction is third order, which brings us back to the orders, rate orders. Thirdly, let's look at the most common one, the rate law represented in form of concentration and time. Notice that we can represent the rate in the form of disappearance of reagents being nitrogen and oxygen versus the appearance of the products being nitrogen dioxide, which is simply concentration over time.